So right at the beginning, I really want to express my gratitude to the ICAM because we started many projects. It was very fruitful, and I've made many contacts. I probably will for this for a very long time. Many collaborations, and specifically, and that's what I wanted to say. I recently got this professorship at the Federal University of Rio de Janeiro, and I'm very sure that the ICAM fellowship played a very important part in that. So the idea of this talk here is, of course, that I give a summary of everything that we've done. But as I already have mentioned, we have done many different projects. So right at the beginning, I want to mention some of them, which are actually finished or very close to finishing. So we have found linear and temperature resistivity in ytterbium close to Lifshitz-Bell installation condition. We have done the Characterization project, which we are starting to write up now, and the superconducting thermognetic ground state in certain types of spin valves, which I will present here in a poster. And besides the colors, there's a second difficulty that I already encountered. So I ordered this poster to be here today, but it will only arrive tomorrow. So I hope that it will arrive in time to put it up, and then I can talk about that. So I decided to talk here about this strontium titanate project, in particular, by the way, it's also cut off at some point. So that's nice. About the strontium titanate project, because it is definitely, of all the projects, the most ICAM-ish. So people from both institutions have been heavily involved, but also certain equipments have been used that were only available on each of one. I don't know how many times we had to send samples back and forth. So it's for sure very adequate. And one more thing I want to mention is Jaime Oliveira, who was a master's student at that time in Elisa's group. And he went to Cambridge within this project for a month to do experiments, and he made a very good impression. And now he's doing a sandwich PhD between the CBPF and Cambridge, which of course is also an indirect consequence of this ICAM fellowship. Yeah. So strontium titanate is a perovskite, and it actually has a very long history. It's a very famous material. One of the reasons is that it's a displacer quantum ferroelectric at low temperatures, and you don't find that very often. It has very high, extremely high dielectric constant of 25,000, and the dielectric constant is proportional to the Bohr radius of dopants that you put in. So you can easily metallize the normally insulating material in a very low number of dopants. This is already very interesting, but what is really surprising is that it becomes superconducting at extremely low electron densities of 5.5 times 10 to the 17 per cubic centimeter. And then if you put in more dopants or more electrons in a different manner, then you will reach a maximum TC of 400 millikelvin, and then it will drop again. So you have something like a superconducting dome. So why should anyone be interested in a superconductor with such a low critical temperature? Well, as a matter of fact, due to its diluteness, it is generally thought of to be the superconductor with the strongest interaction between the electrons of all the temperatures. So if you could create a material which shows the same type of interaction at higher temperatures, that would be spectacular. And you actually, if you reach the normal electron concentration, you would be easily in an area of room temperature superconductivity. However, it's doubtful. So one of the properties which is actually responsible for strontium titanate being so interesting is that it has a ferroelectric quantum critical point at negative pressures. So if this can be done experimentally, so if you substitute the oxygen with an isotope, then you can tune to there have been numerous attempts to explain superconductivity. Most of them somehow failed in that specific material for different reasons. The first one was the multi-valley DCS, so if you had several valleys, then you could increase TC, but as a matter of fact, strontium titanate has only one valley at the gamma point. So our approach is based on the Jelly model of Wadin and Pines. So if you look at the interaction of the, normally on the Coulomb interaction of two electrons in the undoped material, then you write it down the frequency-dependent version, and then you put in the dielectric function dependence of frequency and Q, and you can write it out so you get a function for the Coulomb potential that you actually can plot, and where the zeros actually correspond to the transverse optical and the longitudinal optical mode. So you can see now if you soften the transverse optical modes, they will go to 0. Actually, you will get huge areas of an attractive interaction for low frequency. Actually, in the most extreme case, you would even get a static extreme attractive interaction. So now, however, if you now put more electrons in the system, what will automatically happen is that you will screen these electrons. You can do this with a random phase approximation. So here you see the potential that we just wrote down, and then you can put in with the linter. I don't have a laser on you. We don't. Doesn't matter. It's okay. It's okay. And what you can see here now, if you put more electrons in the system, so and for the 10 to the 19 carriers, you find huge areas which are blue. Everything's blue a bit, but now huge areas of blue which are attractive. And the more electrons you put in, the more you will screen the polarization of the phonons, and what will happen is that you don't get the areas that are formally attractive. So this gives us qualitative. This gives us a qualitative understanding of why we have a superconductive dome, right? So superconductivity sets in, of course, there is no Fermi surface, you put a few electrons, and then at some point you have a Fermi surface, and then you can have superconductivity. However, for high carrier densities, the electrons will screen the interaction, and what will happen is that superconductivity is not possible anymore. So this, of course, is related to the fact that the transverse optical phonon modes get close to 0, close to the quantum critical point, which is at negative pressures. Logically, if this idea is true, when you now apply pressure, you should be able to suppress this interaction with very low pressures. So this is what we have done. So what you see here now is for a sample of 2 times 2 to the 10 to the 19 electron per cubic centimeter. So in the range of actually before the dome peaks. And you see now that already at 6 kilobar, we were able to suppress superconductivity completely. And this is a very impressive result, because usually with such low pressures, this is quite a strong effect, which very well relates to the quantum critical point. So now we can plot the phase diagram of strontium titanate based on this. So this is the data from the paper that I showed with the oxygen 18 substituted samples, where you can have here now the ferroelectric quantum critical point with the ferroelectric area and the paraelectric area. And this is a bit difficult to understand because it's not projected in. So we have very low electron density, so we now put it into the same graph. And you see now how we have this behavior where we see that the superconductivity is strongly suppressed, quite low pressure density. So this means that, to summarize that, the suppression of the transverse optical phonons near the ferroelectric quantum phase transition leads naturally to a very strong interaction, a very strong pairing interaction for the electron. So from that model, you get just naturally the superconductivity without putting too much in. And the effective interaction due to the polar phonons is easily screened by putting in electrons. So one really important thing is now, is this interaction possible? Is it possible to transfer this interaction to other materials where you might have a higher critical temperature, where you have higher electron density? Probably not so much in the case of materials that are close to a ferroelectric critical point, but maybe to materials that are close to an anti-ferroelectric quantum critical point, which is less sensitive to the screening of the electrons. Otherwise, there have been experiments where they put iron selenide on strontium titanate, and they could raise easily they would have raised the critical temperature by a factor of 10 or something, or 8, I think. And so this might very well be related to the coupling to the modes in the strontium titanate. Yeah, I talked a bit quickly because I always said that everything was great, but yeah. So thank you for your attention.
Questions? Can you go back to the phase diagram?
Yes, definitely.
So, what is the phase that extends to 25 Kelvin at negative pressure?
What is the phase that exchanges to 20? So this is a ferroelectric phase. So if you have a non-doped material, then and you would put it into negative pressure, or you substitute alternating, then you go to ferroelectric quantum critical process.
Karen.
I'd be interested in I mean, there are a few women. I'd be interested in seeing the experimental results on the phonon dispersion after pressure or under pressure.
Yeah.
You have done, or can you tell me something?
No, we have not measured. We have not done any measurement of the phonons under pressure. We have done only these measurements until now for the resistivity data. Yeah. But no, you mean for the negative pressure?
Yes.
Ah, no, I don't
No,
think that
you put 6 kilobar and you find that the TC is strongly reduced. So I'd like to see how that pressure
relates to the
effect, how it relates to the phonon, and maybe to the optical phonon.
Yeah, we haven't measured that yet. I'm actually not sure. No, we haven't built it. Yeah.
So that was a negative pressure because, as I know, usually by increasing the pressure, the TC increased.
Yeah, so I mean, this is if you have a classical BCS superconductor without putting anything. This is what you would expect. So I mean, in this case, we related it to the quantum critical point. So that is one of the reasons why you suppress it so heavily. Actually, far away from the quantum critical point, you don't have soft phonon. You don't have the soft transverse optical phonon modes, and thus you wouldn't expect to have any superconductivity of that type.
Do you have simple interpretation on why you have two different TC curves of the different substitutions?
Two different TC curves?
One which goes twice.
Ah, you mean like for the so okay, let me go back to the let me go back to the slide. You are talking about this superconducting zone. No, there is a very strong variation in the literature on the TC. So I said that it peaks at 400 millikelvin in this one slide, but it's actually, you find there are some papers where it peaks at close to 1 Kelvin, so it's really varying. So, and no, I'm not aware of any change in that.
I was a little bit confused by your talk because you talked about transverse phonons going soft, and yet I thought that an optic phonon is not a transverse phonon. It's a kind of phonon where atoms go in opposite directions, whereas a transverse phonon.
Yeah, no, but we have transverse optical phonon modes. I mean, that's no. I mean, of course, just send in this direction of the transverse direction they go against each other. That's normal.
So, but all optical phonons are transverse. So
No, they are in higher energies now.
okay, so in this case, you're sure it's a transverse mode that's going softer.
Yes, and it has been I didn't talk about the other interpretations that you find in the literature, but there are people who have related it to directly to the coupling of the transverse optical phonon modes. It's a superconductivity occurs. But So I can't remember right now what was the problem with that. It is in the Takala paper. I know. But of course, in this case, it's very different. In this case, we do not couple to the transfer of the optical phonon, although it is related to the transfer of the optical phonon that go to zero. Yeah, so this is, yeah.
You can back there already.
Is this the same system for which Balatsky and Spondin and others were predicting a large isotope effect, a large increase in TC with oxygen substitution?
Yeah, that's the
So,
same.
have you looked at that?
Yeah, actually, that's, yeah, I mean, this is what that's the pre-experiment, but this is by doing oxygen substitution here.
We didn't show TC going in that direction.
Ah, yes. Ah, yeah, okay. No, that's true. So that's true. Yeah, they suggested to do that. So it's very complicated to make these crystals, of course. So no, we didn't do that yet. But yeah, this is what you would expect, actually, if you now go to and substitute the oxygen, you go closer to the quantum critical point, you would expect a higher TC. Actually, they have even made a prediction on how far they can say this.
Okay. Let's see. Yeah. Thanks, Sergey.
I come back to these two curves. Apparently they have the same slope at the beginning, and then the maximum is different.
Well, I wouldn't say that this is necessarily true, because
Because
this is now, the temperature is on a linear, both scales are linear now. I don't know if you could plot them logarithmically, it might look a bit different if they're really the same slope. But if these samples are created, I mean, one of the big difficulties of the experiment, the huge difficulty was that we found that we haven't proven that yet, but it seems that there is a phase segregation, at least to the surface. Yeah? So you kind of have clustering of the dopants. I don't know how it is with the oxygen reducer because we didn't try that, but it's very likely that this will create strong effects in the TC because the basic model remains the same, but whatever.
Other questions for Carsten? Okay, well, thank you very much, Carsten.
First of all, so I want to thank the ICAM to give me a chance to study at Rice University. And so first, I co-work with Houston University. But then another year, so I transferred to the LP. Right? So today I will talk about the structure, composition, and superconductivity in the area Chalcogenides. First of all, so I want to cite some previous calibrator. So here is some my previous boss. Some of them come from China, some come from Tokyo. And here is in the last 2 years, I worked at the Rice University, and another one, so I worked with some professor who here about the neutron experiment, and finally, thanks to the ICAM. And about today's talk, so I want to talk here almost 4 parts. First, I want to briefly introduce the area-based superconductivity. And the second one, so I want to talk about the structure and superconductivity. So we use the sodium to intercalation of this kind of superconductivity. And the third one is we found there's a new kind of the ammonia ions. These ions have been intercalation between this arid compound. And finally, so if we have enough time, so I will talk about new results about some possible ferromagnet in the arid compound. Okay. So as we know, so the area-based superconductivity comes from the 2008. So this is the area-based superconductivity, the first area-based superconductivity. You can see it's typical, it's a layered structure. So once the ground state has been, once this compound has been doping, so the ground state will surprise the superconductivity just show up. So after almost 80 years, we can see the area-based superconductivity. So now it's a very huge family. So this is just the sum of them. So one common feature, they have the same layers showing here. This one is the so-called the conductivity layers. But it's another layer, so we can change a lot from the one element to these very complex layers. It's another feature showing here, we can see, so once this area-based superconductivity was applied by the doping of the pressure, so the ground state were surprised. There is a doomed superconductivity showing here. Okay, about the now, so the area-based superconductivity, this one is a very hot topic. It's so-called the Enderlein-based superconductivity. So the first one, you can see, the first one, the area one system is so-called a one system. The crystal structure is very simple. Showing here, just the two layer. Showing here. So once the pressure is applied, you can see from here the 8K. So the TC is increased from 8K to almost 40K. So this one is pretty new results. So just showing this one is
I've been sitting all day.
One thin film layer, just one thin film layer showing here. The TC is around 100K. This is very huge, very huge TC. So this is the just very simple diagram showing how the TC of the Enderlein family, the TC changed. You can see from the 2008, here is only 80K. Now it's already showing 100K. But so we have notes. So this one you can see the very high TC is just come from the thin film one, it's not the bulk one. So the highest TC of the bulk sample is around here, it's around the 50K. Okay, so in the 2010, so we do some work on this one system, and we use some kind of the potassium to intercalate the one system. So we found that the TC is already increased from almost from the 80K to around the 31K. This is our, so we already, we also grew the single crystal, and so after we grew the single crystal, so we co-work with our group, and we got this Fermi surface showing here. You can see there's no hole pocket, and the gamma point. So it means so why the TC is so high. So there is no very general conclusion about this one. So another experiment. So we do some high pressure measurement on this sample. We can see it's around 12 GPa. There is a second doom showing up. So the highest TC is around 50K. But so about this sample, there is a very bad feature. It's about the so-called phase. The phase is mixed. So it means this one phase is the real superconducting phase. It's another one, it's mixed. It's another semiconductor phase. So up to now, so even it's already almost 6 years, so we still don't know which phase is the real superconducting phase. And so for us, so we want to do some experiment to find so which one is the real superconducting phase. This is the work 2 showing here. So as we can see, it's around 2012 and 2014. There is two papers showing which phase is the real superconducting phase. So this is the same film. We can see they got so even in the same film, they also got there is a mixed phase. One is this one is so-called 1-2-2 phase, another is the 2-4-5 phase shown here. This one should be the real superconducting phase. This one is just a semiconductor. So from the back sample, they also got the similar result. So in the 2012, so there is a new report. There is a report. They use some kind of the chemical method. They use a low temperature ammonia method to intercalation, and they just choose this lithium and sodium and the potassium. They got a lot of the superconducting phase shown in the blue one. So now, up to here, so there up to 2012, there is still no very clear clue about which one is the superconducting phase. So we do some work about, you can see this color change, right? Change to the black, okay, change to black. So we do some work on the sodium system. So we found there are two more phases shown here. So one phase shown here is ammonia-free phase. So even we use the ammonia, but we didn't find any ammonia in the sample. So we call it the ammonia-free phase. This one is the 1-2-2 phase. It should be the real superconducting phase. So there is some figures from this paper. You can see this is the 1-1 phase. This is the 3 phase. This is the 3 phase we got, and we can see from here. So the interlayer spacing has increased from the 5 to 11, and the superconductivity showing here. There are 3 phases. One is the 37, another one is 45, another one is 42. And we also confirm the crystal structure of the 2 new phases. So one phase is one is called 1-2-2 phase. So the very important thing here is we found the ratio of the iron and the selenium is almost 1-1. So it meaning this phase should be the real superconducting phase. It's not the 0.1. So it's not the iron. So it's around 0.7, 0.8. And so after we got these 2 phases, we also examined the phase, why the phase is so stable in here. So we can see this curve showing the phase. So containing of the ammonia, we can see the phase is pretty stable. So it's up to 0.5. So but with the new phase, the 1-2-2, we can see the phase is very narrow. So we also found there is a report in 2013 showing that once the selenium is totally changed to the sulfur, it's already changed to another 1-2-2 phase. It's not the tetrahedral phase. So meaning this one is pretty narrow. The phase range is pretty narrow. So there is another clue. So we can find here is the role of the ammonia. So why this sample is so stable? So we also do some new experiment about this one. And here we found there is a new type of the ammonia ions, and it's shown here. The results shown here. So this figure, is showing the crystal structure of this intercalation sample. you can see here, so it's just one layer of ammonia, but here it's already changed to two layers of ammonia. This is our results. So we use the barium and ammonia and the Enderlein to treat the sample. So after we got the sample, you can see the TC is almost the same as the previous one. So the TC is the same as the report one. And here we found there's a new type of this one is ammonia ions found here. So basically, so the effect of the ammonia ions is similar as with the potassium. It's also docked electron to the Enderlein layer, so the TC can increase. So after we go to the crystal structure, so so we want to find why the TC is so high. Is there any very close relationship between the crystal structure and the TC? Yes. So we found there is some closing here. This one is our phase. So compare the other three phases. So the TC is very low. So this three phases is already have been these three phases are already reported. So we found the crystal structure showing here, and the most important thing here is showing the TC have the correlation between this angle, the angle 1 and the angle 2. You can see it's showing it's a very good relationship. So we know it's almost 6 years ago, so about the 1-1 phase, they still showing a very close relationship between this selenium height. The selenium height, so it's meaning the angle. So it's the same as this angle 1. So once this one is decreased, the TC will increase. Also, we found very close relationship between the TC and the distance of the iron. This one is also consistent with the previous result. So after we got this trend, right, so we want to know why. So here, so we co-work with just some theoretical guys. Just we got this band structure. We also got the Fermi surface. So this from the A to E, we just increase the angle. So we can see the two features shown here about the band structure. So one feature is from the A to E, you can see the band is very, so it's the band is more broad here, shown here. It's meaning so the band's enhancement is very small in the E case. It's another thing that we found the Fermi surface change. So from the B to F, so we found from the F we found there is a very important thing about the pockets from the M endpoints. This interaction may be important. So actually, so we found there is a new paper. They already measured the real Fermi surface of the 1-1, so the 1-1-1-1, so 1-1 compound. We found a very close Fermi surface compare our calculation. So this Fermi surface change, so it's contrast with those of the iron peptides. We can see in the iron peptides, so the Fermi surface, so it's very the interaction between the gamma and the M, so it's very strong. Even the TC is very high. Okay, so finally, so I want to introduce our new results showing here about the new superconductivity of the iron sulfur. So in the 2015, is a new compound has been reported. They use the hydrothermal method to go to this phase. There's a new paper showing here. This one is also showing the second doom on the high pressure. So we use the two-step heterothermal method. So we grow the single crystal of the iron sulfur, so we can see the TC. So it's consistent with the previous one. So here, so we also do some powder neutron experiment. So we found that there is possible this phase is ferromagnet. So even in the 300 K. And from this one, the magnetic structure shown here, and we measure from the room temperature to the base temperature 5 K. Yes, it's still ferromagnet. But so there's a new paper just 2 weeks ago. They found that the guys they use the μSR, they confirm they distribute the anti-ferromagnet. So it's totally contrast with our result. So that's what we think about. So maybe we prepare the sample with the hydrothermal. Is water and all water is very easy to contaminate with the sample. Maybe this is the reason. Okay, so the first this is a small summary and open question. Okay, thank you very much.
How stable they are to process in air, or should you have some care?
You mean the iron sulfur or
Yes.
So the stability, so this one is very stable. This one is very stable, even in the room temperature, even in the air and room temperature. And about the previous one, this sample, so it's very, very unstable. So even in the room temperature, so you must keep it in the blue box or the vacuum. This sample is very, very unstable.
Over the slide, if I open questions very quickly, we'd be lost.
Yeah, you also previous probably 10 minutes over, right? Yeah, the open question here. So I mean, basically there are two questions. Why the TC of the intercalation sample is so high? You know, the bulk sample, the 1-1 sample is around 8. But so when you intercalation some of the molecular between the aerosols here, so TC is around 40 or 50 K. So, but so about this series sample, we only got the powder sample. We don't have the single crystal sample. We don't know, so we cannot know why the TC is so high. But the second one, now we have the 2 PhD students. They are doing the inelastic experiments. So about the iron sulfur sample. This one, the iron sulfur, the crystal structure is the same as the iron cyanide. But this one, just the new sample, the new single crystal we got. So we want to do some inelastic experiment to find maybe why there is TC when it's superconductivity. So how the TC correlation between the spin fluctuation. This one. So we got this sample maybe 1 month ago. So we got time and